Nope. Pause. That's a reaction. That's a reaction. I was really hoping you would do that. Thank you for making that mistake for the team. Okay. Ammonium nitrate solution process.
You add water.
Add water. Okay, either add water. I wouldn't actually add it as a reactant. Like it's a solid, right? Add it as a kind of, hey, I'm here. I'm liquid. I'm going to help make this thing dissolve. Dissolve it.
H2O3 is just going to ionized back out.
Why are we making H? What'd you just say? So that's what. So Alvin wanted to say ammonium hydroxides and nitric acid, right? But when you do that, you're basically reacting it. And when you react it, yeah, you do have to consider NIE. So yeah, the H plus would ionize because HNO3 is a strong acid. Ammonium hydroxide necessarily isn't a strong base, so that's why I really don't want you to react. I just want you to ionize it.
So this is just dissolved.
Just dissolves. Makes what?
Okay, ammonium nitrate.
Ammonium ion and nitrite ion, or nitrate ion, sorry. So yeah, I just want you to see that the solution process is just like our KSP examples, because you guys, we're trying to hit some review as we go. So when you have your KSP, you always take your solid, you make your two aqueous ions, okay, and then you move on. And if you want to do a double-headed arrow for a KSP example, like I could have you set up KSP and so forth, but we're just talking about aqueous solution process right now. All right, magnesium sulfate. Ready when you are. MgSO4. Arrow.
Mg2 plus.
Okay, which of these is used in a hot pack? All right, which is in a cold pack? Does anybody remember this from our little hot pack, cold packing free lab we did?
Isn't magnesium used for the hot one?
Magnesium is a good example of a hot pack, yeah. And a lot of times magnesium metal or iron metal, things like that are solids, can interact with oxygen to make hot pack as well. So this process is delta H. This whole solution process for the second one has a delta H of what?
Negative.
Negative. So delta H of solution, the whole shebang, is negative. So if I'm telling you one's hot pack, one's cold pack, this one up here must be delta H of solution as positive. It's an endothermic process. But, and this is what I think I don't remember, maybe it was Courtney told me, the solution process has 3 steps, right? You read about that in your reading from an SMI? So the 3 steps, H1, H2, and H3, all combine to make that total solution. So that's kind of what we're talking about for now. And then we're going to go over some of the examples. So this whole solution process requires us to do 3 things. Somebody tell me one thing that it requires. Like this right here, ammonium nitrate. What do I have to do to it? It doesn't just, like, it's not the same at the end, right? So what did I do to these 2 ions? I did put them in water, but remember, I'm making them, okay, what was this? Okay, so I basically overcame the ionic attraction. So I broke the ionic bond. First, you have to do that, right? So first step, break solute. And I'm going to say break solute, a lot of times you do mean it's ionic. It could be covalent as well, though. Second, water is just all up on top of water, 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 water. How is all the water attracted to each other? Hydrogen bonding. So first we have to break this ionic situation up. Then the water doesn't intermingle with the ions just immediately. We have to break the water particles into their individual water particles. Am I actually breaking water atomically or molecularly? No. The water is still attached. It's still H2O, but I'm overcoming IMFs. So after this has happened and this has happened, then they start to come together. And so when they come together, that attraction process between the ions and the water, that's really, 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 really energy lowering. And so there's a combination of putting energy in to break the ionic structure, putting energy in to break the water's intermolecular forces, and then releasing energy when they come together. So that's our process, and I have a slide on that. Same thing down here, but overall we have a different energy perspective, right? So why is this one positive overall and this one negative overall? Why would that happen if this is the sum of all the steps?
The energy that's released when the water bonds with the ions is greater than the energy required to break both the hydrogen bonds and the ionic bonds.
Okay, so the energy released, well, I'm going to call it H3, okay? So the energy released at the last step when they interact is greater than the energy it took to break the ionic structure and the hydrogen bonding, okay? So I like it. So that's happening here, which is, that's happening here, because that's why it's a negative overall. So then what's true about this top one?
It's the opposite.
It's the opposite, because I have to have some sort of reason for this to be positive overall. So both of these processes have a delta H associated with them. Do you guys remember the 2 driving forces to reactions to like why a reaction actually will occur? Basically the two factors that play into delta G. So the spontaneity is what we were saying when we say delta G, right? So what two factors play into delta G?
Delta H.
Yeah, delta H and delta S. So delta H is here. So we got one endo and one exo. What's the most favorable sign for a reaction to occur in terms of the enthalpy?
Negative.
Yeah, so the spontaneous reaction, delta G, to be negative, for that to happen, you can always depend on delta H being negative. That would force delta G to be negative as well for the spontaneity, but what would the delta S have to be? Positive, meaning what? More disorder, right? Okay, so if I'm telling you this is a positive and this is a negative delta H, what's the delta S's for both of these? Positive or negative? Why? What's delta S measure? Disorder. Isn't the disorder increasing? Nice, pretty crystal ions. Nice, pretty crystal ions. So we can see the disorder is increased. So do you think both of these processes are thermodynamically favorable or spontaneous? They could be, right? What if I told you they both happen? Okay, so if they both actually happen, like we can make a cold pack and we can make a hot pack out of this. They both happen without really a lot of intervention. You're just putting them together. When you like pop a cold pack or pop an ice pack, you're just breaking little inside baggies so that the two chemicals actually mix together because they're isolated individually at first. So if they both happen, but these are positive, positive, this is positive, negative, there has to be something else kind of at play. So usually a temperature component will come in, which is why delta G is equal to delta H minus T delta S. Also, the spontaneity or the disorder that's increased because of this whole ionization process, this might be huge compared to the amount of energy that's going to take it, which might give it that overall negative aspect of the end. So there might be a difference in the measurement of disorder of this. Okay, so that kind of hit some review with thermodynamics and solution stuff, and then I have like a little picture down here for you. Does this matter? At this point, no, it doesn't. Okay, so more kind of related to that process. I'm going to do a couple of the notes that I didn't get to yesterday, and my people can listen to this on video. So this whole solution process, we kind of just orally went over the thermodynamics of it. Again, what are the two driving forces of reactions? So entropy, which is delta S, and enthalpy, which is delta H. And so they both have to interplay together to give us an overall delta G of negative. Okay, cool. And so the whole entropy aspect is coming in from these ions being attracted to the solvents and so forth. So this is sodium chloride dissolving with the water. All right. Oh, and so why does the solution process even occur in the first place? You guys know a little bit about IMFs. There was one new one that we had not discussed yet because I was waiting till we actually were talking about water, like in solution form. So the ion dipole is actually the strongest of the strongest. Okay, so we have a tearing effect here. Who's the weakest intermolecular force? LDF with London dispersion just between two nonpolar molecules, and it's because of Coulombic attraction. So Coulombic attraction force is equal to. Okay, I'll do that partial. So actually, I'm just going to put Q because I want to show the different parts here. So Q positive, Q negative over what? Distance. Okay. So the distance between all of these molecules is probably going to be about the same because molecule 1 and molecule 2 are not going to be that much different in their like general like positioning. But what's different between all of these molecules that I have here to show the difference in the strengths of the IMFs is that these partials, are those a big partial negative and positive or a small partial negative and positive? Pretty small because these are nonpolar molecules, so the only way they get their partials is just because of that like really quick electron being shifted to one side versus the other, like tiny partials. So when you multiply those together, doesn't make a huge impact of force of attraction. But when you start getting down here, why are these partials greater? Why is there a bigger partial here? Because you have a polar molecule, yeah. Polar molecule, you have a dipole moment pointing one way, and so this is more partial negative on each of those sides and less or more partial positive on the other side. Just because of the polarity difference. And why does the polarity difference even occur to begin with? Your group, trends. Oh, yeah, change in electronegativity or difference in electronegativity. So even greater partials, even greater force of attraction, right? That's dipole-dipole for you. And then hydrogen bonding, why does it have a stronger force of attraction than dipole-dipole? It's fun, but tell me more.
It's like a super strong dipole because like the hydrogen's pretty much guaranteed to give you some electron.
Good. So this right here, I'm going to draw it from this way. So this is an even bigger partial negative and partial positive, even bigger partial negative and partial positive, even bigger partial negative, partial positives. And it's because H has like basically no electronegativity, 2.1 electronegativity. And fluorine, good golly, 4.0, heck yeah, it's going to be shifted that way. And the same thing, oxygen and nitrogen are pretty high on the electronegativity chart as well. So even bigger partial positive negatives make an even bigger force of attraction between the molecules with their distance that's separating them. You see how everything relates back to Coulombic attraction? That's great. And then we have the big boy, the full-on charge of this ion. So this is where we have something called ion dipole, which I didn't introduce last time because it wasn't really relevant for anything outside of solutions. So if I have like big old magnesium here, 2+, attracted to this little partial negative of, what is that on the water? Say it again.
Oxygen.
The oxygen. Partial negative, okay, times a 2+ charge over the distance. Ain't nobody got anything on that positive charge. That's a two full positives versus your partial positive. That's why ion dipole is so much stronger than the rest of them. Does that make sense? All related to the math of it. So my math people, that's your saving grace there. So that's why we order these in accordance to dispersion, dipole-dipole, hydrogen bonding, and ion dipole. It's not the distance that separates the molecule. The distances are all about the same between all of these molecules here, 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 and here. It's really just the force of attraction that differs, caused by the partial positives or full positives. Sorry, the partial charges or the full charges that differ. Okie dokie. All right, so that makes a lot of impact when we're talking about solutions. Can I move on? Yeah. So this is it. Okay, thanks.
What's the difference between that and
An
ionic?
ionic, because ionic has like a true, this is in solution, of course, like an aqueous solution. So this is going to have an ion with 6 waters actually that surround it. So that's a really, really, really strong attraction, but not nearly as strong as like sodium would be if it were bonded to chlorine with a 1-. So this ionic bond is stronger than these ion dipole moment attractions, simply because these are actually really, really close together. So their distance being smaller means their force of attraction goes up. These are a little farther apart, so the distance is bigger, so the force of attraction goes down. Good question. All right, so just remember intermolecular forces come into play with solutions, as do entropy and enthalpy, so a lot of driving forces to make solutions actually occur. And that relates to why things don't occur too. Like, what's a good example of a precipitate? Insoluble product. Silver fluoride. So this I know as a silver 1+ and a chlorine 1-. They're pretty well attracted to each other. Why is that more attracted to each other than water? I do not have an answer for that. I think it's because it's just a heavy metal. I was going to say like magnesium sulfate, but 2+, 2-. Never mind. All right, so many times the charged products can actually give you some indication. What about silver phosphate? Silver phosphate, what's the charged product? 3. It's a strong attraction for each other. The charged product is kind of like the numerator of Coulombic attraction. Okay, so why do things actually end up mixing either solution processes in aqueous solution or not? It's all about going towards lower energy overall, so lower potential energy. A lot of times correlates with an increased entropy. And so you can see that naturally argon and neon here will mix, and the reason why is because they end up having lower energy overall, though they have higher entropy, which is our disorder. We talked about that yesterday, and there's my polar bears for you. I mean my grizzly bears, not polar, non-polar. Is all that new? I mean, is all that old news? Yeah. The only thing that's really different is that we can talk about solutions in aqueous form, and then in just in generic, like, hey, 2 things are mixed together. So you can have gases being dissolved in gases, liquids being dissolved in liquids, and solids being dissolved in solids, which is really weird to think about. But think back in earth science, how are solids and solids mixed underneath the ground? What's the rock that mixes together?
Sedimentary.
Sedimentary is when they layer on top of each other just by deposition. Metamorphic. So metamorphic or igneous. Igneous is formed through hot molten processes as well, like in volcanic kind of areas. So both of those can form different mixtures in rocks, which is just a solid-solid mixture. And then liquid solubility, of course, will be related to like their polarity and do they actually intermingle. The only thing that's weird with gases is if they don't If they can't stay together, they won't mix. So that's why carbon dioxide, which weighs what? Carbon dioxide, which weighs what?
44.
44 grams per mole. And oxygen, which weighs, don't say 16,
32.
32 grams per mole. Oxygen will stay up high, CO2 will stay down low, and so they do mix, of course, but like if you have a lot of CO2, it will kind of plummet out, which is what smothers a fire. So the densities of gases can kind of limit their miscibility sometimes. Closer in there, molar masses can cause them to be more buoyant and kind of mix together. We haven't talked about soap yet. I just saw this really good V-Cell study on soap. I'll have to find it. Okay, you guys know how soap works? You guys know it has a piece that has an end that's polar, that's non-polar. So this is actually, that's not my soap molecule. Here we go. So this little guy here is a soap molecule. Okay, this is what, according to the structure or the image. Okay, so some oil substance, oil with like fat and grease, right? What's a little zigzag line usually mean? But what's it in organic chemistry? Well, carbon. Okay, so carbon everywhere, right? So if this whole thing is carbon, is that going to be polar or non-polar? Probably non-polar because it's not going to have any kind of difference in its functional group. So this non-polar region will stay really, really well attracted to the oil because it's mostly fat and non-polar as well. What's this little piece out here then if it's intermingling with all the water around it? A polar or non-polar end? A polar end, and that polar end it's basically, they say it's a hydrophilic group, and that hydrophilic means water loving. So water, hydro, like loving, and so that's what that right here says. And then basically they kind of surround a bunch of soap molecules, will surround a piece of oil or fat or something, and they'll wash it down the drain when water normally wouldn't be able to do that. So that's how anything works, like detergents. Detergents actually have enzymes in them as well, but also how soap works for like washing dishes, washing your hands, anything. Okay? So it's called a soap micelle when it forms a little circle around it to kind of like bombard it, but it's really just the big piece I want you to know has a polar end or a polar end and a non-polar end. Kidoki?
Pretty silky, Is it like really nasty stuff?
No, it's just carbon chain and a phosphate group. It's really similar, or glycerin, like this big zigzag here is like glycerin. So I thought I had here it is right here, yeah. So the hydrophobic chain is here, and then we have oxygens, and usually it has like a phosphate or something like that over there, and then it can have like a sodium or an ion there to keep it that end polarized, because it'll kind of stop somebody else from giving out extra electrons. So it's kind of interesting. All right, so this will be the last part I'll do, which is our solution process we introduced with, and then we'll do two labs in the back. All right, so this is probably one of the most important pieces that sometimes you have to explain on the AP exam or see a picture. I have a picture down here that will help. So label down solution process: delta H1, delta H2, delta H3. This week and then like next week has some note heavy days, so calculate yourself. We're towards the end, man. We're gonna do some calculations too. I wish you could just absorb everything. If I could just connect to like a USB from my head to your head, but you know, maybe not that far yet. It's my idea. I'm the patent it first. Stop.
Nope.
If I could program, I could do it. Maybe. My dad wants me to invent something. He keeps like throwing ideas at me. I'm like, when do you think I have time to invent something? He wanted me to invent something for like electrically conductive gloves that would also exist with your own heat.
Gloves?
Yeah.
They're not shocky.
Well, that's what they have to be insulative and then also use your own body heat to. Yeah, it's interesting. I was like, Dad, no, I can't do this. Good times. All Alright, so I know you're writing down the details here, but this is our first process that we spoke of earlier. Separation of solute, and then Alvin, what was your symbol for separating the solute? So what does this mean? Blah. What does it mean, guys? Okay, so it's going to be endothermic to overcome ion to ion attraction, so breaking ionic bonds, or if it were something covalent, maybe it would separate, but most of the time this is going to be in regard to ionic aqueous solutions, so making an aqueous salt solution. And that is going to have to require energy, so it's endothermic. Separation of solvent molecules is just overcoming, like if it's water, we're overcoming H bonds, hydrogen bonding with hydrogen bonds with other water molecules, because it just needs to make space, because if not, water is just all up on water, and it's really, really well attracted to itself, but not so much other things. So that's, of course, overcoming, putting energy into that process takes some energy to do, so endothermic again. But then we have that really great mixing at the end, and as the ions come into contact with water, what do they form? Ions come into contact with water. Ion dipole. So all that ion dipole attraction, which is really, really strong, right, makes it very, very stable. So the ion dipole part of this is really causing quite a bit of stability, and it happens 6 times for every ion, because water surrounds one ion 6 times, or 6 water molecules that surround 1 ion. So that's very, very, very exothermic, and so occasionally, if this is so exothermic, it's basically supersedes that, making the overall process what? If this is really, 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 really exothermic. Okay, so overall, for a delta H solution, which you have delta H solution, they're total here, add those up, you get delta H solution, which we opened up with today. And then if it's not as exothermic as the others, then you're going to have an overall endothermic process, but it still happens because of the entropy differences. And these images here give you an idea of what that looks like. Yeah?
Why does it surround the ion 6 times?
Because of the way, it's just the way an ion, okay, so like that ion in the middle, I don't know if you can see this, there's 1, 2, 3, so there's 4 greens, 1, 2, 3, 4 in this plane, and there's 2 in this plane. As to how their lattices form, it's how they have space for 6 attractions, basically.
So it always forms 6?
Generally water with an ion. And so that's why it's so, like, crazy high in terms of exothermicity, because of the whole attraction part happening 6 times. Okay? So this is your overall break up, expand the solute, expand the solvent, mix together. So that's kind of a good image there. And they had this almost exact image on the multiple choice a couple years ago. They released their sample. So, and then this is my favorite image: attack of the water, attack of the killer water molecules. So they're coming in. They can this is a really strong lattice structure: sodium ions and sodium. That's the chlorine. Sorry, chlorine negative and sodium 1+. Oops, on this little blue one here. But the 6 water molecules can create so many ion dipoles that they do actually attract it. There's only 4 shown in there, but it's usually 6. And so overall, the process of solvation, not like salvation, but solvation can be really, really, really energy lowering because of the attraction, so electrostatic attractions, which is stabilizing. So those partial positives on that water and then the full positives on the ions create that whole considerable energy lowering process to happen. And there's a bit more to this, but I want to make sure I stop now because I think you guys are tired. I can't always stop when you're tired, but I see you. I see you. And so delta H1, delta H2 can be lesser in magnitude than delta H3, so it's going to cause it to overall be exothermic. But what if delta H3 is less exothermic than H1 and H2 together? Overall endothermic. Will it still happen? Only if delta S is high. Yeah, if you have a high amount of entropy. Okay, entropy has to overcome the endothermic nature of this. Okay, let's check number 2 on your problems from last night. Because the math side of this I thought would take us longer, but if you guys know your formulas, you really don't need a whole lot of help there. Normality is the only thing I know. I'll do all this stuff tomorrow. So this was your big slide of information, but this was in your packet as well, how to calculate everything. We did a sample of this yesterday. If you watch the video, Lucas, there's an example of me doing this whole shebang out. So the normality part is only really regarding acids and bases, where you actually have to look at the amount of H+ given off of the acid or OH given off of the base. So it's really similar to molarity. So normality is really similar to molarity. It's just if you have an acid that's a diprotic acid like sulfuric acid, you'll multiply it by 2 because of the 2 H pluses that come off of the acid. Or if you have sodium hydroxide, it only has 1 hydroxide, but if you have calcium hydroxide, you have 2 hydroxides. So you take your overall concentration molarity wise and multiply by 2 because it's more based on the component of the acid that makes it an acid or the component of the base that makes it a base. So basically consider the number of H pluses or OH minuses, and that's what you're considering the molarity for. But that's number 2, so I'm going to do that as an example. Okay. Yeah.
Is it, when it says, like, say the number of H plus or OH minuses, is that per molecule or?
Like per mole.
Okay.
Mm-hmm. So like if I found this to be 1 molar sulfuric acid is actually 2 normal sulfuric acid because it has 2 H's. Or 1 molar calcium hydroxide is actually 2 normal calcium hydroxide because it has 2 portions of base. All right, so that question, is this it? Yeah. All right, so how did you guys start this? Tell me like your knowns, like the given piece of information. I know there's only a couple.
Molarity and density.
All right, so molarity actually gives you 2 pieces of information. That's what I need you to see. Molarity, which is 3.75 molar sulfuric acid, actually gives you what over what? 3.75 moles to be specific. Oops, sulfuric acid over what? And you get to assume 1 liter of solution. If it doesn't tell you anything for volume, assume that. Right, so it gives you 2 pieces of information. What else is given? Density of the solution as a whole. Okay, the entire solution is 1.230 grams of solution over 1 milliliter of solution. So remember to label it water solution individual component because it does matter when you start to mix this up some. All right, so if you guys want to find mass percent first, what do we have to put on top? Like, what's the numerator going to have to be? Your acid. So grams of acid, which is sulfuric acid in this case, over what? Grams of total solution times 100, right? All right, do we have grams of acid? No, but we have moles of acid, so we can convert that, right? Okay, so take your 3.75. Somebody get their calculator because I'm counting on you.
It's 367.7. The molar mass is 98.9%.
Thanks. I was like, whoa. I can do math, but it's not 98 point what?
0.76.
Okay, and what's the total?
367.8.
785, okay. Alright, so square off and or highlight your math as you go. Okay, so those are grams. That's going to go on top here. And then what goes on bottom?
1,230.
How do you get that? Uh-huh. Okay, so I'm just going to write that down here. So 1 liter times 1,000 milliliters. And the density is 1 milliliters, 1.230 grams times 100. All right, so this down here was what again? 1.230 grams total solution. Math. 0.299%. Did I get that? Or 29. Yeah. Okay, good. I was making sure I have my book from here too. 29.89%. Okie dokie. It's getting messy here, but you can see how one piece can just domino effect and give you more information to go with. All right, so we have our mass percent, but we had to find our grams of H2SO4 and our total grams over here. So then molality means what? Whatever what?
Moles of solute over.
Moles of solute, which is H2SO4, over what?
Kilograms of solvent.
What's our solvent? Water. Okay, I already can do that. What's our kilograms of water?
Because I need 0.860.
How are you getting that?
with your 1,230 grams of solution,
Mhm.
that much solute.
Okay, that much solute. So then what are you doing mathematically?
You subtract the 367 plus 230 and increment it in grams.
Ooh, okay, so this is our grams total. This is our grams of just the solute. Minus that gives you 862.275 grams of water. Yeah, and then convert that to kilograms. So that is 0.862275. Oh my gosh, kilograms of water. All right, and then how do I get moles of H2SO4? Oh, we already have it. Look, right here. So if you, as long as you're labeling your work and kind of go back and check, you can find your stuff really easily. So 3.75 moles of H2SO4 divided by that. What do you get? 4.35. Well, how do you say M? How do you say little m? Malal. Okay. All right, so good so far? And then normality is the last part. Now, I could ask you the molarity, right? Molarity, you'd have your moles, but what would be your denominator? Liter solution, I already had that. Did I get a molarity? No, sorry, mole fraction. I was thinking mole fraction. How would you get to mole fraction?
Moles of the solvent.
Solute.
And then the additive moles of solution solvent.
Right, and so how would I get moles of solvent?
862 just divide that by 18.
Right, you can convert water to moles and then add them to your denominator. So once you have one thing, it's really easy to get the other. Okay, normality now is just going to be, I'll give you two options here. Normality is this, but with respect to the portions of acid here, which how many portions of H plus do I have? 2, so you just take that times by 2 to get 7.5 normal. Or you could actually take and say, okay, that makes 2 times the amount of H plus, so it makes 7.5, like I could say 7.5 moles of H2SO4 or H plus, and just divide it back by the liter. In the end, it will work out. Yeah.
So you won't see like normality for anything that's not like acid base.
True. Yeah, that's the only time you ever see it. Okay, guys, works out. You good? All right. The next couple, I might say for my crew that's coming later. So like it's exercise 3. I think you guys are probably good with that. For Henry's law, if you use Henry's law, which when I'll do it tomorrow with you guys, it's just using the equation. It's not hard. The vapor pressure one though, we're gonna spend like 30 minutes on because vapor pressure in itself we need to probably practice some more. So we have about an hour left in class. 30 minutes for each of the activity that you're gonna do. Go on a desktop, since there's a couple of us, so groups of 2 or 3, or 3. You guys want to do this table to table? Go to polymer. I'm gonna have you guys write down some feedback for me. I'm gonna tell you what this is for. Polymer education kit. Just Google polymer education kit, and it'll be the first link. No, not this one. This is more for us to experience together. It's one of those. Polymer education kit. All right, so look up here as you go. Alvin, we put that little bucket back in the back lab station. So basically, you guys know I've worked for UNC Charlotte for some time. I'm still working for a professor, and we're publishing a paper at the end of this week. And so I told him I would run the lab for the, like, whatever time this is I'm running this, in my classroom because we need some more data to just kind of get some student feedback. So when you get here, this is a website I created. It's not wonderful. Like, I'm actually going to redesign this website. So if you have any tips or any feedback, I'm good with that, because he said old white men have no idea what this little thing up here means, but you guys know that means there's stuff there, right? You click that, there's stuff. Okay, so yeah, polymer education kit. It's gonna say polymer semiconductor kit. Sorry, if you just Google polymer education kit, it should come up there. So yeah, that's me. And then I was paid to design this like two summers ago, and we're trying to get it to like a couple big universities. So under students, if you click on students, you can see there's 3 kits. So we got it on Google Play, but Apple is a beast. So there is an app you can download on Google Play, but Wi-Fi is also, I know you don't want to do that right now. So the first module is called polyaniline nanofibers, student lab, and you guys can click to expand it out to full screen. And you can see this is all me. So pre-lab, look through stuff about doping, look at some of the examples, it's pretty cool. A little extra reading with oxidation and so forth. But then the real part of the lab starts under lab 1. You guys will make your samples, and it tells you exactly how to do it. And if you have who has a QR scanner? Thank you. So you can scan the QR code and it'll give you a quick little video on how to set up the lab itself. It's about a 1-minute time-lapse video. You'll recognize some of the people in the lab or in the videos. So after you guys do the part 1, you'll probably get to part 1 and part 2. You may not get to part 3 on this first one, but that's okay. So back to the student website, you'll see it says module 2, polymer LED. Polymer LED is an organic LED. And so under here, it gives you some information again on the LED, so student laboratory. First, you'll construct your LED, and then you'll test it for emission and fluorescence. So that'll be the next part, but it does require the fume hood because it has a compound called MEHPBV, and MEHPBV, it has chloroform in it. You guys know what chloroform is used for? Never mind, please on me. So knocking people out. So not good things. So there's a pre-lab section, but I really want you to actually look at everything. You don't have to do all the pre-lab questions. You don't have to answer everything throughout. But look at it and go, this is too much. This is over my head. This is too much, or this is not enough information. Something that gives me valuable feedback. So I'm going to publish this paper with this. So your responses will be used for the greater educational community. That should be using Wi-Fi. That's a LAN connection. Huh? Maybe it's Thanks, Levi. Alright, so open up those two labs there first. Start reading module 1, and I'll bring you guys your scripts. Can you get a piece of paper? Maybe just line feedback on. You can explore the website too. I'm finding out. So send somebody to come over here and grab some materials.
oxidative synthesis.
Oxidative synthesis, yeah, that's what I'm doing.
That's the one. Okay. Actually, I didn't even know we can.
What I was telling you, it's right here. I was telling you one of these, I'm running across this, some people working for now, is steel, okay? Other than close it back up, really check it afterwards, and I'll have you be careful and I'll be checking it.
Yeah. I should do too.
So, I'm gonna give you guys a possible this to do with shaking. Okay, so give me a second, start that. Get your masses out, and I'll give you multimeters as well. Okay, so we'll take your 2 multimeters with them, and the next group series. Bring your group gloves, please.
Why are we watching this?
So basically you're making something called a bio or a sniffing device. So the sniffer devices will have this conductive polymer on it, and it's this like little green stuff you're going to be making, and Levi's watching the video there. And so that has the ability to detect really small particles, well, like scent particles, things in your composition phase. So we're going to dope it, and we're going to look for conductivity differences. So that's what you have to read the background a little bit, but now you're running blind. Your feedback will be less valuable.
I just watched. Yeah, he's gonna shake his camera and all like I'm
That is the demonstration of how you shake. That's all that is. Maybe it's yeah, Jack is my sister for that particular summer.
Did we just? Oh.
Follow it to the key.
Okay, go ahead.
Yeah, Mr. Oliver, educator, Mr. Dexter, for my area is non-lab. You go to the next class. What are you doing?
on the back file, or is it paper? Paper. Do you have a microscope available? Do you know if that's any carefully cases that oh yeah, some kind of error. That's very good. Thanks.
There we go. Oh, that is it.
All right, so you guys are on the part where you're synthesizing first, so read really carefully, and then do you look through things to give valuable feedback